Yeah, so this is the X, Y, but we use the measure of section place. The function of X and Y must be the function of X and Y. X, Y is the 0 is 0, 1 year, X is equal to 1. And then the 0, all the and under this is 0. X is b of X plus Y plus b of.
Okay, sorry to interrupt the discussion, but let's get started. First, let me just quickly go over the upcoming deadlines. I sent an announcement about this on Monday because that's when we shared your intermediate report grades. The final project report is due next Wednesday, so only a week from now. So I think all of you are on a pretty solid track. If I had left notes in spirit of it's still not clear what exactly are you trying to do and how are you measuring that you have either succeeded or not with respect to that goal, please make that very clear very soon and try to work towards that such that you have results for your specific goal reported in your final report. This is important. I mean, it's very important in both research and in any other setup that you know what you are doing and that you're showing whether you have succeeded in that or not. I know this is all kind of new now, so you're not really sure what exactly that is. And if you're still feeling unsure about what you're trying to show, then you should definitely reach out to me, come to their office hours after this lecture today, or just send me an email and we can schedule a little meeting. After that, we are going to submit your poster outlines on Monday, April 17th. And then we will quickly just check whether that looks okay and give you a feedback if there's something really needs to be changed. And this will all need to be done in a very timely manner because on the 19th, we must batch print all these posters to have them on time. Yeah. That's a good question. Probably A0 would be a good dimension, either vertical or horizontal. So yeah, let's shoot for max A0. Yeah, and then on the 24th, we will have poster presentations in front of the front desk on the 3rd floor of the Merrill Engineering Building. So yeah, your question kind of prompted me that I should probably also send some notes about what exactly we should do here. I was kind of expecting that also you probably will first write your report and then you'll make a poster as well because one leads to the other as well. All right, any questions about all of that? Okay, let's then continue with our lecture. So last Wednesday, we were talking about different things. We mentioned linear discriminant analysis, and then we had moved on to distance metric learning. And we have just started with that. We haven't proposed any algorithm or anything yet. We have just said what is the motivation for this line of algorithms. We were talking about how most of the algorithms we have seen assume that all our features come in the same units. For example, you have temperatures measured in Celsius degrees, let's say. And when we have features that have different numerical scales, then things can get very funky. Some of our algorithms simply won't work because they assume Euclidean distance. And as a trivial idea, we had talked about what if we just try to normalize them all to the same values. And then we talked about different things that might happen here, either some very, unusual values, making this normalization strange, or we can even add some dummy features, which when we normalize them will be as important as all the others. So normalization is not the best thing one can do here. And that was our motivation for learning the Mahalanobis distance, which is defined with this equation. So we take almost like an outer product, that we have this matrix M in the middle. And if we didn't have matrix M, we would have Euclidean distance. Matrix M is D times D dimensional matrix. That's positive definite. And I kind of assumed all along that you do know what positive definite means. I kind of realized maybe it's good to bring the definition just such that you see it once. It should be very familiar from linear algebra and also from calculus, because you use positive definite matrices to find minimums of higher dimensional functions. In any case, if we are defining M to be positive definite, that's the same as to say that the following thing is satisfied, that if you take any vector x times M and then again x, you're going to get something that's positive for all x that are in R here D without 0. This is a little bit, I don't know, maybe too abstract. If we would really like to know kind of more geometric intuition behind this, this just says that this term here is going to produce a quadratic form, which is basically a quadratic function when we have higher dimensional inputs, and that's going to be a positive value. That probably now is too obscure, but if you put it in the context of optimization, it becomes a little bit more appealing. Very often you are going to see something like this. If M is positive definite, then we'll say that M is symmetric. And all of its eigenvalues are real and positive. All right, so if matrix is symmetric, so M is symmetric, that means that Mij equals to Mji, so it's symmetric across diagonal. And alternative to not having real eigenvalues is that eigenvalues are complex numbers. And alternative to them not being positive is that they are either negative or 0. If we have semi-positive definite matrix, then here instead of strict inequality, you can also include 0, and that's the only difference. So if for now this is slightly overwhelming, just know that this is a class of matrices that have very neat properties and are useful. Here specifically, it's useful because if we have such matrix M, then the Mahalanobis distance is going to be a metric. And remember the properties of the metric when we had the lecture on distances. Those were that if we are having a distance with the distance of a point from itself is going to be 0. We have the positivity that distance is always going to be positive values. We had symmetry that the distance from one point to another is same as from the other point, distance from A to B is same as distance from B to A. And we also had transitivity. If you had a point in between, we said, if you are going from home to work, it's easiest to just go that route if you can, let's say, fly. But if you are going to stop and have coffee, then a distance from home to coffee shop and from coffee shop to work is going to be larger. So that's why the M here being positive definite is useful. Okay, so the goal is to learn such matrix M. We don't know what the values of matrix M are. We are trying to learn them, find them, and then we can define this distance by just having this equation, right? And then when we introduced this, we had set up this max-min problem with the constraint. So we said that we first of all define far and close points. So we define a set F to be a set of pairs of points from X that are far away from each other. This notation X times X just means you take a point from X and another point of X, and that's a way to write that you are taking pairs of points. So we have F here. And then we have, on the other hand, close points. So we have C to be a set of pairs of points from X that are close to each other. And we used it in the constraint. Okay, so let's try to read this maybe more like outline. We are trying to find a matrix M such that the distance between far points is minimal. And we are also trying to, excuse me, I said something that's very confusing. So we are trying to find M such that the minimal distance between 5 points is maximal. So if you are maximizing minimal distance, all other distances are going to be even larger, right? Yeah. Oh, I don't know, but we can maybe try. Oh, that's a little bit too dark. Bench. Okay. Is this better? That's all I have from the options over here. Yeah, I think this one is just for people. Yeah, sorry about that. If something is not readable, just raise your hand and I will try to read it out loud. I don't know how to turn this one off. The one right above the screen. Do you see any other switches maybe? No. Sorry, yeah. Sorry, second?
Is that less than or equal to 3?
Less than equal than kappa, yeah.
What is that?
Okay, we'll read it now, but let's first focus on the main part. All right, so here, let me just maybe write some points. Okay, here we have some data and maybe here. Okay, so these 2 points, these points here are all far points. So this point is far away from this point, this point, this point, this point, and all these other ones are also far away from the points on the right. So all these points here are far away from these points here. But the minimal distance between pairs of far points is this one. So I will delete all the other ones here. So this one is the one which is minimal distance between far points. And if we are going to maximize that minimal distance, we are effectively maximizing all other distances between far points. So maybe it's slightly confusing to say max min, but it is in the end maximizing the distance between far points. Now we have this constraint over here. We're not just interested in maximizing the distance between far points, we also want to minimize the distance between near points or keep it in check. We don't want it to now accidentally grow too much. And then we didn't achieve this thing we wanted, and that's to learn a metric. A metric should be such that far away points have high value of this metric and close points have small value under this metric. So this constraint here is just to keep us in check, to maximize these distances between far points, but to keep distances between close point bounded. And we use some hyperparameter kappa here. So this is a thing we need to choose. In our next derivations of our algorithm, this is going to be 1 because it has nice mathematical properties to turn this whole optimization procedure into something else. Okay, any questions about this? No. All right, so our goal now is going to be to turn this huge optimization function here with the constraint into something that's more feasible. So we are going to recast our optimization problem into an optimization problem that's equivalent under a certain values of kappa, and that's actually solvable, at least approximately, with iterative methods. Think about gradient descent, not exactly gradient descent, but something of that sphere. So we are going to have an optimization procedure later on. All right, so let's work toward recasting our optimization goal. For that, we are going to need to introduce a bunch of notations. So bear with me. We are going to fill all of this with math. And please, if I don't look at you and you don't see what I'm writing, let me know and then I'll repeat. Okay, so first we are going to define a set, delta, that was very ugly delta, to be all vectors of the size of however many points, far points we have. So remember, capital F was set of far points. So we will have a vector that is of dimension of the size of the set of far points. And this vector is going to have properties. Basically, it's going to pretend to be a distribution over far points. So what we want is to have all of these values in the vector to be in a sum 1. And we want all of them to be equal or larger than 0. So no negative. So this is in a way to say we are defining a probability distribution over far points, or not really. I mean, it needs more stuff, but it's kind of pretending to be that. Here is a mistake. We don't have n. I'm writing that out of habit. The size of the vector is this, how many far points we have. So cardinality of the set F. Okay, then we're going to define a set of our positive semi-definite matrices. That's going to be written as this fancy S. We are going to have plus a subscript and D in the subscript just to denote the dimension. So this is going to be a set of all positive, just a moment. Positive semi-definite matrices. Of size D times D. And we are going to then define a little bit special set of such matrices. It's going to be set of all positive semi-definite matrices of size D. But we are also going to require that the trace of this matrix equals to 1. Remember, the trace is the sum of all values on the diagonal of the matrix, so sum of all MIIs. And we didn't show this, but you cannot see immediately, but you can find in the literature that people have shown that this is equal to the sum of eigenvalues of this matrix. So these are two the same things, just same ways of calculating the trace. And we want the trace of the matrix to be equal to 1. Okay. The reason why we are introducing this is because such matrices M that have this trace are effectively going to imply this, this constraint. We are not going to show that, and not for any kappa, but for kappa that equals 1. So if we are choosing matrix M to define our Mahalanobis distance, so M is the part of the equation, then the sum of distances under that matrix M for close points is going to be smaller than 1 if we are setting our matrix M to be positive semi-definite matrix whose trace is 1. So that's why we are now imposing the trace to be 1. All right, then we are going to introduce more things. We are going to have capital H to be sum of outer products of close points. So xi, xj are a pair of close points. So they are in a set of C, which is set of close points. And we are taking the outer product of the vectors that we get by taking the difference between them. So xi minus xj, xi minus xj transpose. And as always, this is going to be D times D matrix, because if you are taking an outer product of D-dimensional vectors, you're going to get D times D matrix, and we are summing all such D times D matrices, as many as there are in the set of closed pairs C. Okay, we are then going to define x tau. Tau will be a way to present or denote our far points. So tau is element of F. And we are going to take the outer product of x tau, which is xi minus xj, xi minus xj transpose, as well D times D. I will just quickly delete this. I apologize for that, just to make the connection between the indices I and j more clear. So we call this tau, but it's actually tau ij. So it's a far point xi xj. All right, and the final thing we'll need is, I promise, the final thing, x tilde tau. We are going to take our h. We are going to calculate h to the power of 1 or minus 1 over 2, and we're going to multiply it with x tau, and then again with h 1 minus 2. Now, all this is doing is we are taking this x tau is our outer product between far points, and we want to use that to say, oh, let's maximize this. But at the same time, we have that constraint, and we want our close points to stay nearby. So basically, what is doing is kind of scaling down the outer product such that the constraint that the close points are close stays is going to happen basically. So the scaling happens just such that far points are far, but close points should be close. And now all of this together will give us a way to recast our original optimization problem. Any question about this stuff? Yeah. C is a set of close points. So we have our data set, some are far, some are close, and these are the ones who are going to be close.
Right, so we partition our data set into F and C.
Sorry, second?
Do we partition our data set into F and C?
We want to learn a metric where when we calculate distances between close and far, and however we define what's far and close, this whole thing will be preserved. The distances between close points are going to be smaller than kappa, and we are going to maximize the far points distances. But I think the confusing part is that we didn't get to the algorithm yet. So when we come to the algorithm, from the algorithm, we will get the partition. But so far, we are just kind of talking about these things as we have them while we are still not having them. Okay, so we have introduced a bunch of things, and the goal the purpose of introducing a bunch of these things is to recast the optimization problem over here, which is computationally not great to tackle, into something that we like computationally more. So that was the purpose of all these simples over here. This is just repeated stuff. Okay, so let's now recast this. So all of this now, given our newly introduced symbols, is going to boil down to this. We are going to find argmax over M in our fancy set P. Fancy set P was the one of all semi-positive definite matrices, all positive semi-definite matrices D that have trace of 1. So we are going over all of those. We are finding the one that maximizes the minimum over vectors alpha in our capital D, which were the vectors that basically were giving us distribution over far points. And we want the sum over all far points to where we sum their weighted products with x tilde tau and M to be minimal. So x tilde x tau was this scaled outer product between far points. So think outer product between far points that kind of keeps the distances between close points in check. And you are going to multiply that with matrix M. The way you are going to get the scalar product between matrices is similar to how you would do it with vectors. You are going to multiply each corresponding item in these matrices and then sum of all of them. Maybe I can write this down. So x tilde tau M. The scalar product, you will go over all indices ST, and you're going to then take the value in the matrix tilde x tau in position ST and multiply it with the same position in the matrix M. Okay, so what does this thing have to do with this thing? So remember, I told you, and I will not go into details of that. First of all, I changed here, kappa was here before, I changed it to 1. And the reason I changed it is because I said, if we are constraining ourselves such that these matrices M have trace of 1, then the effect of that is going to be that we are satisfying this constraint. So this constraint, we don't have a constraint anymore because this was given by the fact that we have chosen M to be in this set fancy P. Now, what does this minimization of the distances, maximization of minimal distance between far points has to do with this? So now we are maximizing minimal scalar product between these two matrices. But remember, this matrix tilde x tau is defined through the outer product of far points. So in a way, we are doing the same thing, right? You can see that. We are trying to maximize the minimum distance between far points, and that distance is captured by the tilde x. And remember that Mahalanobis distance is defined like this. So you have all the ingredients of your distance matrix. So maybe it's not 100% mathematically clear how we get from here to here, and that's not my point. I didn't show you those derivations. I just want to make clear that you get a sense of how this thing here is connected to this thing here. Is that to some extent clear that these are similar? Yeah.
What do you mean by very
far points are far. So far points are those that Oh, excuse me, there is a typo here. Yeah, so here we mean by far. And do we have far? And okay, I think that's the last one. So if you see fair, I mean far, and feel free to remind me that you see it again so we can cross it out. Yeah, and to repeat again, we don't know what far points are yet. It's kind of a thing we are going to figure out. Okay, so this problem here is nicer because it can be tackled with the techniques we have. But to use one specific optimization technique, we are going to need to produce what is called a more smoothed version of this problem. So to do that, let me just write something down. So here, this thing here, this min over vectors alpha such that minimize this function, I'm going to call that f of m. All right, so we are finding the argmax over m when we use this function m, fm. And now our next thing is to find smoothed version of fm. Okay, so I will just show you what this is. The smoothed version just includes this additional term, and it will make this function such that we can differentiate it a certain amount of times. And this all comes from this paper over here. So if you are interested in any of these details, this is the place to go. To recap what we have done so far, we have our main optimization project problem, the one that's general for any kind of distance metric learning. We have found equivalent optimization procedure, and to be able to use a technique for optimization that I will introduce in a second, we have also needed to smooth out this function f here. And the smoothed version of that function f, this function f, comes from that paper. And I'm not showing you how we get to it, I'm just showing you what it is. It is this term. It doesn't really matter what any of this is. And we are now going to, our whole optimization procedure is going to be to find matrix M that is in the set of in a set of positive semi-definite matrices that have trace 1, such that they are maximizing this function, which itself is a minimum of something else. And to find the maximum of that smoothed functions, we are going to use Frank-Wolf optimization algorithm, which is also known as conditional gradient method. Can I see how many of you are familiar with gradient descent by raising hand? Okay, decent amount. So just quickly, gradient descent is a way to optimize the function iteratively if we assume function is convex. So we have something like this, and then if we have a function like this, we know that and we are looking for the minimum, which is over here, we know that we should go in the direction of the steepest descent, and that's exactly what the gradient gives us. So if we are moving in the directions of steepest descent, we are going to eventually get to our minimum. The difference between what we need to optimize and what gradient descent gives us is that we have certain constraints. And another way to kind of go about doing optimizations with something like gradient descent is to just project your solution to your optimization problem to whatever space you are looking for. So you are finding where you need to go, but you are also considering that whether you are in that set or not. And Frank-Wolf is just another algorithm to do something that projected gradient descent is doing. It basically is going to let me maybe show you with a sphere. What it's doing is, imagine you have your set where you want to find the solution for your optimization problem to be this circle. And let's say your current in the current iteration, you are over here. Then you would take the gradient, which gives you direction where you should move, but then you're going to just project it to the circle. Oh, this is very small, I apologize for this. So you find where you need to move. Okay, you need to move in this direction. That's gradient of the function f in a given x. And now you want it to be on this circle, not inside the circle. So you are going to project it to the circle. And that's your solution in the current step. I don't know how to write it, xt plus 1 maybe. Not the problem, but this is a nicer setup than if you have sets that look something like this. Now, the solution that's going to optimize your function is not going to be the one that moves. Let's say this is the gradient. It's not going to be the one that's over here. If you know something about this kind of optimization stuff, you know that it's going to be one of these edges, and it's going to be exactly that one. So these Frank-Wolf algorithms kind of give us these solutions to these kinds of constraint optimization problems. And someone else has shown that this Frank-Wolf algorithm optimization algorithm or procedure can be extended to address optimization problems we have. And those are semi-definite programming over the cone of positive semi-definite matrices with trace equal to 1. Sounds very wordy, but the point here is that the optimization problem we have is exactly the one that has shown in this paper that we can address if we extend this Frank-Wolf algorithm. And this extension turns again our problem into an eigen problem, and it's then solves this whole thing approximately. We don't get the exact solution, but when we opt for any kind of iterative methods, we usually do not get the best solution. Otherwise, we would have closed form solution like we had with the linear regression. So now when we take all of that together, we are going to get to our algorithm. So I just want to quickly go over everything we have said so far. So we had our original optimization problem. We have turned it into an equivalent optimization problem. And it has been shown in this paper by Hazan in 2008 that this Frank-Wolf optimization algorithm can be extended to solve the problem, the exact problem we have here. Not exactly that, but the smoothed version of it. And this extension introduced in that paper will introduce some eigen problems. Is this kind of line of what has happened somewhat clear? Again, the purpose of what I'm saying is not that you understand all of that. It would take multiple lectures. Just kind of how we get to the final thing I will show you. All right, I guess hope it is. All right, so going back to our smoothed version and our optimization problem with our smoothed version, with these optimization iterative approaches like gradient descent, we are going to need a gradient. The gradient of this smoothed function f is this big term over here. And basically that kind of brings us to our algorithm, which is known as either approximate Frank-Wolf algorithm for distance metric learning, or as a DML, which stands for distance metric learning, for eigenvalues. So here in this algorithm, you're going to give the number of iterations, which we always give if we have optimization procedures such as gradient descent. And you are going to need to also specify that smoothing parameter. Usually that's set to some small values such as 10 to the power of -5. And you're going to initialize your initial matrix to be any matrix you like from that is positive semi-definite and that has trace 1. So one such matrix could be M, where you have 1 over D on the diagonal. This is a symmetric matrix, and it also has real positive eigenvalues. Therefore, it's positive semi-definite. It's actually positive, not only semi-definite, positive definite, but all positive definite matrices are also positive semi-definite. Okay, so we are setting our initial matrix M to be this, and now we are going to, in every iteration, change it a bit, such that in the end, after our capital T iteration, we get our final matrix M. And to do that, we are going to calculate the gradient, this thing over here. We are going to then find what is the maximum eigenvector of that gradient. And this is that extension I was talking about. This is how eigen problems come into play. And you're going to define ZT to be outer product of the eigenvector corresponding to our largest eigenvalue with itself. And you are going to update your matrix such that you are taking the your matrix in the previous iteration and updating it by this outer product of this eigenvector you have found. Okay, so that's it. After the theta iteration, you're going to return your matrix. In any kind of optimization algorithms, we usually have also give some kind of whatever, let's call it epsilon, maybe like a change parameter, where you check whether your MT plus 1 and MT are sufficiently different under some norm. And if that difference is too small, then you say, I'm not changing anything anymore, and I think it's a good space to stop. You can imagine if you are here, if you come to this valley over here, when you can't move too much because you're kind of stuck, right? So this is basically what's happening. You came very, very close to exactly where your gradient is 0, and now you're doing these small changes which don't bring you anything. It's like throwing the computational resources you have. And we would call this early stopping. If you are not changing what you try to change too much, you just stop. In machine learning, typically we use the loss calculating on the training data. If your training loss didn't change much, you say, nothing to do for me here anymore. I have learned everything I have from this data. So sometimes you would have T to be very large and you set certain epsilon for yourself. Okay, I recommend that if you are interested to learn a little bit more about optimization, to check this YouTube video, which will kind of show you how taking this basically linear combination between the matrix M in the previous iteration and this ZT gives you both the minimum. It's kind of pushing you in the direction of the gradient, but it's also finding that that point in your set that is the closest solution. So think about this circle I have drawn you. You are moving in the direction of the gradient, but then you need to do this step where you are actually finding the solution that's in the space you're interested in, which becomes more complicated when you don't have circle, but rather this polygonal stuff. Okay, and there are 2 libraries for distance metric learning. These are 2 of them. In this first one, you will find this algorithm under the name DML-EIG. And the other one doesn't have it as far as I know. And the other one is it is implemented in a way that's more compatible with scikit-learn. So if you need other distance metric learning algorithms and you're kind of accustomed to scikit-learn, that's could be a good library for you to check. If you're interested to learn more about other algorithms, I recommend this tutorial, which has a bunch of them. It's very nicely written. And then this other one is also has maybe less comprehensive overview of everything, but the way these algorithms are described in this second paper is really neat. And it's very easy to follow. It might not give you all the math derivation, but it really gives you impression of how we got to the algorithm from which kinds of objectives. Okay, any questions about distance metric learning? Okay, and maybe just as a kind of last point, to be sure that you kind of grasp what we are even doing here. Once you have learned this, these matrix M, what do you do with it? You go back to your Mahalanobis distance, right? You are now defining distance through that matrix M. So now you have a distance. And if everything went right, the far points are going to have large distance, this one specifically with the matrix M you have learned, and close points are going to have small distance under this matrix M you have learned. And this can be good for example, your clustering. Remember, we have in clustering, the gist of it is this distance matrix. When we talked about k-means, we have used 2-norm, but you can replace you can use the distance that's more suitable for your own data. And that could be this one. And now you can have better clustering because you are using better distance to start with. But there are many other reasons why you would do this, including the problem with the normalization, like your features not being in the same units. Okay, I know it's a lot. It's a little bit more complex topic relative to other ones, so it's fine if not everything is super clear here, but I hope the main ideas are coming across. Okay, so I would like to switch to another topic. So last chance for distance metric learning. Okay, so we are going to now, for the rest of this lecture, talk about we are going to talk more about outliers, but outliers are connected to something that's called noise in the data. And you can have noise in your data for many reasons. You can straight up have just someone adding to your data malicious inputs. So this is a very prominent line of work in computer vision, especially. It's kind of trying to be a thing in NLP as well. So there is something called adversarial examples where basically you can add, I don't know what's funny. You can add to your, let's say here you have a image classification task. You're trying to classify these images. You have trained your model and you give it this image of a panda and it will have with with some moderate confidence that's panda, so you're happy, but you are giving some small noise, which is here moderated by this variable epsilon, and now you have to our eyes, to human eyes, image that looks exactly the same, but the model will be totally thrown off by it and say that this is here given, and it will have very high confidence in this misclassification. So this kind of examples where you add these small noises that are not perceptible to human eyes, these are called, but that are going to fool models are called adversarial examples, and models that, or techniques that produce such examples are called adversarial attacks. And then you can measure stuff like adversarial attack success rate and so on. So your data might have noise, and that noise might be deliberate. Someone might actually try to add the noise in your data. This is also related to stuff like data poisoning. Then you can have measurements error. For example, I keep mentioning this weather stations because I think it's the easiest example for me. But if you had your weather stations all having very corrupt machines, like they are broken, they are super old, all of a sudden your measurements might be slightly noisy, but slightly noisy in each feature. And this is slightly different. It's first of all, no one is attacking you, and also every single feature is affected. And then you might have problems with like background data. And here you might have problems where, for example, you are getting some other information mixed in that's not really relevant for what you're trying to do. And now it's kind of noise because you don't really need it, but it's there. And these kind of dimensionality reduction techniques were in a way useful for that, right? Remember when I was talking about multicollinearity and I said some features might be even predicted from the other ones. But you can also have a problem where you miss data. So, for example, and we'll get into that, if you are Netflix and now you have your data metrics where in each row you have a user, a movie or whatever TV show, and in your each column you have every single one of users you have, then a lot of the values are going to be missing because I don't know about you, I don't rate anything on Netflix. So if I'm user in their column, my column would have a ton of missing values. So this is also kind of, in a way, is part of this category where your data just is not having everything you need. Okay, so these are kind of different types of noise you can think about. It's very hard to categorize every single noise there is, but you can at least think about these different categories. And one of them is also outliers. These are the examples in our data that are just very different from the others under some definition of differs. And today, for the rest of the lecture, I want to talk about how we could kind of find and remove outliers, very, very simple approach. And also, I will talk a little bit about density-based approaches, especially in the context of clustering. I will not cover these. These are in the notes if you want to look into more stuff like if you have just uncertainty in your data and how you could actually model the fact that you know that there is some uncertainty in the data, or how you can go about developing robust estimators. So we talk about how you can find and remove outliers, and in a second I will tell why that might not even be a good idea, and then maybe a more reasonable approach could be that you just embrace the fact that you have outliers and that you need to build a model that's not sensitive to them, instead of trying to use a model that's sensitive to outliers and clean up your data, because that might be hard or even a wrong thing to do. So yeah, let's go into this. So remove outliers. This is the simplest procedure you could do. You could, of course, you will build some kind of model of your data. You will find some kind of representation or whatever. And then let's maybe put it in the terms of regression. You are having your data and now you found the regression model that approximates the how your dependent variable depends on independent variables. And for each one of the points, you can then find your residuals. Remember, we had some points. And let's say we have approximated this data with this polynomial. Then we can calculate the residual for each one of these points. So that would, oh God, that's bad. So here, these are all our residuals. And, you know, none of them are exceptionally different from each other. But if we had a point that's very far away from the others, maybe over here, then our residual would be way larger, right, than all these others residuals.
one axis, or is it like undirected training? So I guess that's because typically I don't want to do like the y-axis visual.
Yeah. So here it's a 2D problem. So we have x-axis, which is our dependent, and y-axis, which is our, excuse me, I is independent and x is dependent variable.
The distance from the line to the line, not like the whole. Does that make any sense?
Oh,
Yeah.
yeah, you're right. Yeah, they are going to be not like this DNA looking thing, but maybe I can start over. Now I'm doubting myself. Okay, we have points, blah, blah, blah. And we have some kind of polynomial. Okay, I was doing projection, but basically what the residual is here, let's say for this point over here, this is y value. And then when we projected, this is the age x that we have figured out, and that's why the lines are vertical, not projections that I was doing. Yeah, thank you for the correction. So here, this is the residual. Okay. And so on. And then again, the point stands. If we had very far away point, the residual would be enormous compared to the other ones. And then if our residual is too large, we would potentially remove our point. And we would go back to our data and actually back to our model and start over, but just having cleaner data. So we would remove that point from our set B and try to fit a better model. Now, I want to say a couple of things here. First of all, you would choose what is too large just based on your expertise, or it would be, I think, really hard for you to say what too large is if you don't have any understanding of what the task is. So, for example, again, with weather station, you probably need meteorologists to tell you if something like is a complete outlier, like our winter in Salt Lake City this year, I guess, and whether you should kind of ignore it because it happens so rarely that your model doesn't need to really consider it. You could also, instead of picking a residual that is too large, you can say, well, I'm going to rank my data, all of the data points with respect to their residual, and I'm going to take the 95% of the data points. So I'm intentionally discarding 5%. I know I have enough. I know that those 5% I have highest residual might be funky ones. And because I have so much data, I don't need to worry about fitting my model to this data. Removing those 5% won't make a huge deal. However, the problem here is that you might be removing data points, data observations that are rare, but are actually valid data points. And this is, I think, especially important if you do anything which has some kind of social predictor kind of situation. If you are having trying to categorize people into something, then most likely if you are doing something like this, you will actually discard people who are marginalized in your group of people. So there are definitely situations where this kind of procedure would be potentially really bad. So my first recommendation is that you do not aggressively remove outliers. So this kind of thing should be not something you do reluctantly. You should really make it, this should be a hard decision to remove these points. That's what I want to say. So another thing you can do instead of you can kind of, do steps 1, 2, 3 without removing P. And then you will get your set of potential outliers. And depending how many you have, you can maybe inspect them and look at them or sample randomly a certain amount of them that you can manually inspect, and then decide whether this makes, whether it is fine for you to discard those. And again, this will likely involve having some kind of expert to work with you. And these kinds of approaches are called human in a loop, where you make a next decision in your modeling based on whatever a human tells you is good or bad. Yeah. Yeah, I mean, I guess I shouldn't say it. I really want to say it, but some of these techniques, like Bayesian inference, I don't know how much we use them still compared to some deep learning stuff, for example. So depends what your task and the problem is. For language task, for example, most likely you won't go that route because you just won't get as good performance without it. But if you're any kind of modeling of the uncertainty of the data and fits your problem and also is not giving you worse performance than more, involved techniques, then I would say, yeah. And this would go under this category of just find the more robust versions of your algorithm. So the first suggestion is do steps 1, 2, 3, and then find your potential outliers and then look at them manually and make decisions. Another, of course, obvious suggestion is that if you have that you want to do clustering, well, there are so many clustering algorithms, and because this is such a prevalent problem, someone else most likely have be thinking about it in terms of the approach you're going to take. So most likely you can find more robust versions of whatever algorithm you are looking for and then try to apply it. It's just they are going to be more complicated, and I recommend always to try simpler solutions as well, just to be sure that your simple baseline doesn't work better than your more complicated solution. And then for one of these robust estimators, and just kind of reading a little bit about it, you can find in the notes that are always on the website, and I have linked in the presentation as well. Okay, so this is very, very simple procedure, but this is basically what you would do to identify and remove your outliers. Now, there are so-called density-based approaches to handling outliers. And the main idea here is that if you have your regular points, they will have dense neighborhoods. They won't be so different from everything else, so there will be something around them. But if your points are very irregular and you have good distance measure, then under that distance measure, these irregular points will be far away from everything else, and its neighborhood is going to be very sparse, which is, I think, visually makes the most sense. If you have your data points and then one is outlier, there is nothing around this guy, but let's say this point here has this and this point in this very close neighborhood. Okay, there is one in terms of clustering, there is one very prominent algorithm that embraces this idea. It's called DBSCAN, and it stands for density-based spatial clustering. It was introduced, I think, in certainly 90s, maybe 96, and it has been very influential since then. But in the past year, it can be also scrutinized, and then whatever is the antonym of scrutinized. So there are these two papers. One of them is DBSCAN Revisited, Misclaim, Unfixability, and Approximation, and won the Best Paper Award. And then in 2000, I believe, there was another paper called DBSCAN Revisited, why and how you should still use DBSCAN. And it's one of the most, of the 8 most downloaded articles of the prestigious journal. So it kind of tells you that it's a thing, right? And it has its own issues and whatever, but it's a technique people like and are like so much that it's caused the Best Paper Award and the most downloaded paper stats. It's also available in sklearn and scikit-learn. So let's go over a little bit how it works. And I definitely recommend reading this paper, but it's all about, or mostly about, efficiency. So this paper says this algorithm is too slow to be useful, and it kind of tells that, basically brings some other theoretical bounds that says like it can't be this fast, and then this other one says like no, it actually can be this fast. So it's all about like whether this is useful in practice in terms of how fast or slow this algorithm is. But another reason why it's kind of a little bit at least annoying is that you need to choose a lot of hyperparameters. And then we'll look into one version that needs less things. So with the DBSCAN, you will first choose, let's call it an epsilon, which will be a parameter which will specify the radius of a neighborhood with respect to some point. And then the gist of the algorithm is that you are going to categorize each point into being a core point or directly reachable or just reachable or an outlier. And then you will take those core points and you will form clusters from those core points. Point P will set to be a core point if at least some value, min points are within distance epsilon of it. So I will also highlight the hyperparameters. So you need to choose what is the minimal distance between them, epsilon, and you want to also say how many of those have to be at least in the epsilon radius around it. So you need to choose these two hyperparameters. Okay, so if you have, let's say, here, one point, and let's say here another point, and then you say min points is 2, and let's say this is less than epsilon, and this is also less than epsilon, and min points is 2, then this point will become your core point. Okay. A point Q is directly reachable from point P if its distance between from P is less than epsilon. So these 2 points are going to be directly reachable from P. And then you might have just reachable points from point P. And these are all points where there exists path between that point and your original point P, and each one of these points in the path is directly reachable from the previous one. So you can have something like this point here. Let's say that this is also smaller than epsilon, but this distance here is larger than epsilon. So you can reach from this point, you can come to this point through this path, but it's not directly reachable because the distance between them is larger than epsilon. And then finally, all points that are not reachable from any other points are outliers or noise points. So if we have this point here and these distances here, this is larger than epsilon, and this one, all of them are larger than epsilon, well, then you can't reach it from any point, and therefore this point will be an outlier. So this is how you would categorize each point. So already from the algorithm itself, you get what the outliers are, but then you can also combine it with clustering, such that you take your core points and then you form cluster from that point together with all points that are reachable from it. So here in this picture, this would become one cluster. So this will be a cluster of points. And that's basically it. That's the whole algorithm. I did want to show you. I didn't. Maybe it's not so useful. This is the paper I mentioned. This is how illustrations of these paths and how one point can be isolated, which kind of I had illustrated in the end. And then I didn't want to write it down because I was honestly a little bit lazy to write this whole thing, but this is the entirety of the algorithm. So if you want to really have the algorithm in like a step-by-step approach, this is it. But as I mentioned, as you don't really need to implement it because you have it implemented in scikit-learn and you can use it directly from there. And then there is also hierarchical version of this. Basically, want your hierarchical clustering that has similar flavor. And then I think it's called age something DBSCAN. Yeah, sorry, can you repeat? Yeah. And I think it's also implemented in scikit-learn.
It's not in scikit-learn.
Hard life, yeah. So maybe don't use. I'm kidding. All right. So yeah, as I mentioned, the algorithm itself has been kind of debated about its time efficiency, but also a little bit annoying thing is that you need epsilon, you need minimal points, and so on, and that also influences how many clusters you have and so on. So there is a lot to be chosen there, which is one of the downsides of the algorithm. Another thing you can try to do is a little bit simpler. It's reverse nearest neighbors. And here you would have your point sets P. And then for every point, you will calculate its nearest neighbor, we'll call it Q. And then you're going to calculate the nearest neighbor of Q called R. And if the distance between P and Q and R is similar under some, again, measure of similarity, here you would probably again need to choose some parameter epsilon, then P is probably not an outlier. Idea is, I think, visually very clear. So here, let's say we have P, Q, and R. So this distance and this distance are not super far away compared to if you had some real outlier over here, where the nearest neighbor would be R. And here, if you compare this line with this line, the difference is really big. And you would conclude that then this point over here is an outlier. Yeah, and this is super simple, I think. Okay, any questions about this? All right, so we have just a few more minutes left. So I will start talking about matrix completion, but I won't get into the entire algorithm yet because we won't have time for it, but at least we can set the stage. And I don't know, I have this very romantic idea that you then continue thinking about it after the lecture and then come like we just, start discussing it together. Okay, I don't actually have a slide for this one. So remember when I mentioned the situation where you have some of your values to be missing? And I mentioned an example of Netflix that's a prototypical example for this topic, which is matrix completion. So we will have as our input some matrix, let's call it P, with all the data, and it's going to be n times the matrix. And in the Netflix example, n will be your, let's call them movies, although now there is more than just movies, and then d would be your users. More correctly, it would be say to number of movies and number of users. So now you have this gigantic matrix P, and as we have already observed, not every user is going to rate every movie. So a lot of values in this matrix are going to be missing. And what you could do is try to just, so here we'll have, so movie 1, and then we'll have user 1, user 2, user 3, user D -1, and user D. And you can say, well, I don't really know what the value is here, but I do know what the values are in the rest of the rows. So I can just average those and say, this is the rating that this person, user 2, would give to this movie. So I didn't mention here these values, whatever, I don't know what ratings are. I think we have 5 stars max. So we can say 1 to 5, where the number corresponds to the number of stars. But we know that people are different, right? So this is not really a great way to say to say that this person would then maybe the average score is 4, and now we say, user 2 would rate this movie with 4 stars, which is actually kind of high. So I am going to recommend this movie to this person. But we didn't consider what this person, how they rated any of the other movies, right? And it might be that this movie is a horror movie and this person hates horror movies. And now we disregarded that, although we have some data about it, and we had recommended this person movie that I would never watch. So average case here doesn't work best. So what we will try to do instead is to look at these values we have. So all of these values that we actually have across all the rows and all the columns. Let's say here we have information. We are going to look at all of them, and then we are going to find whether there are some kind of latent factors in that data we actually had observed. And latent factors should kind of trigger you to think about principal components or singular vectors, because those are the ones that kind of capture the important stuff in the data, where these important directions are not really, they're kind of predictive potentially of multiple things. They're not like just a single feature. So that's the next thing we are going to do. We are going to try to find out a low rank structure. We are going to do it iteratively, and then we are going to have what will be our completed matrix. And then based on this matrix, we can make a recommendation for movies for users who didn't actually rate those movies. And hopefully our algorithm works. And since this kind of emerged from Netflix, you can tell it kind of worked, right? Maybe it's not the exact thing they have today. For sure, they have some kind of neural network in the backbone today as well. But it's kind of where things have started. So definitely this approach can give us something reasonable. And next time, then I will kind of walk you through the exact algorithm, how we calculate that low rank approximation, which will be based on SVD and everything you know. Okay, that's all. Thank you for coming, although it's very snowy.